Have you ever tried to learn a new structural engineering software and felt completely lost? You are not alone. If you're new here, my name is Gabriel. I'm a structural engineer based in Australia, and I help structural engineers to solve problems and build confidence in their career. In today's video, I'm going to show you how you can choose the best software for your needs, an easy way to learn any software from scratch. Plus, I'll share some cool tips on how to go from 2D to 3D analysis without making any mistakes. So let's start with how to choose the best software for you. I get this question a lot. What is the best software to learn? That is like asking me what's the best tool in a toolbox. It really depends on what job you need to get done. Are you building a house or just trying to hang a picture without hitting your thumb? So when it comes to choosing a software as a structural engineer, you're basically looking at two main types of software: a general purpose and a specialized software. A general purpose software is more versatile. It's good for structural analysis and sometimes even design across different materials and structures. Think of it for the design of beams, columns, frames, that sort of thing. Examples of these softwares would be Space Gas, Autodesk Robot, F2, SkySieve, MicroStrand, SAP 2000, and many others. Then you have specialized software. This is more task specific. They usually focus on certain types of structures and materials. For example, if you're working a lot with reinforced concrete buildings or post-tension slabs, you would be looking at tools like Inductor, RAM, or ETABS. These are often finite element analysis software, which means they're usually more complex and robust. Now, you might find some overlap between these programs, but their complexity and what they're best at are quite different. For example, in Robot or Space Gas, you can design a reinforced concrete slab, but SLB Inductor, for instance, is specific to the design of reinforced concrete slabs. It doesn't do anything else. It is a specialized software, so it will have advantages over other programs. So how do you choose the right one? Assuming you've got the budget to invest, I think it comes down to four things. Number one, your needs. First, think about the types of projects you usually work on. If you're doing lots of post-tension slabs and reinforced concrete buildings, then RAM, Inductor, or ETABS are probably your go-to. But if you're mainly handling smaller residential and commercial projects, a general purpose software might be all you need. Most engineering offices will have at least one general purpose and one specialized software. Number two, modeling speed. You want a software that lets you model and analyze structures quickly. Time is money, so efficiency is key. I would recommend trying out the software by modeling a common type of project you typically work on and seeing how long it takes to solve the model. Number three, industry acceptance. Consider how widely accepted the software is. How many other companies are using it? Is it reliable? The more popular it is, the more likely it is trusted and well supported. Number four, integration with local codes. There's a big difference between just analyzing a structure and designing it to meet local codes. You will need a software that does both. If it doesn't have an integrated design module, you might want to look for free tools that just handle the analysis. Now that we have figured out how to choose the right structural engineering software, let's talk about how to actually learn it. I've worked with a lot of standard software packages that are popular in Australia, but to keep things fresh and spontaneous, I wanted to try something I've never used before, so I can show you how I would learn a structural engineering software from scratch. So for this reason, I've picked Structural Toolkit Analysis Package, which is something I've never used before. So let's dive in. The first thing I'm going to do is to upload the user guide to ChatGPT and ask it to summarize the key points I need to know. I'll use a prompt like this. I'm learning this structural engineering software. My goal is to model simple structures and understand the results given by the program. Give him a summary of the most important points I must know based on the user guide attached. Feel free to optimize this prompt. When it comes to ChatGPT, the better the prompt, the better the answers that you will get. It will give me a rundown of the main concepts, things like degrees of freedom, supports, releases, and analysis methods. These are pretty basic, but if you're just starting out, they're crucial to keep in mind. The second thing I would do is to head over to their website or YouTube channel and watch some videos to get familiar with the software. So here's my step-by-step guide. Step number 1, define your model's purpose. Know what your model needs to achieve before you even start modeling. Are you analyzing both vertical and lateral forces? Do you have to model bracings, shear walls, or can you just apply a support and design these elements separate in a spreadsheet or by hand? If you're starting out, I wouldn't overcomplicate things. The simpler your model is, the better. One of the first windows that pop up when we open Structural Toolkit is the shortcuts, and shortcuts are always helpful to speed up the modeling process, so make sure you make use of them. And for this first step, we're going to model a simple steel frame and analyze only vertical loads. So let's start drawing some bars. Control D to start. I'm going to use the snap orthogonal function and then just draw a couple of columns and beams. Columns will be 3 meters high, beams spanning 4 meters. I like when a software has a graphical copy and move function where you can just grab the element and move around. But it looks like we can only input coordinates to copy or move. All right, pretty basic so far. I'm just drawing elements according to the global X, Y, Z coordinates, as you can see here on the bottom left-hand corner of the screen. Now, if we click on any member, on the left-hand side of the screen, we can see all the properties of this member. And this is pretty typical for any structural engineering software. You click on the member and you can see all its properties, right? I want to change the section and material. I'm going to use sections. Currently, we're using a 250 UB. I'm going to create a new section called beam and make it a 150 PFC. Material will be steel. I'm going to create a new section called column and make it a 75 by 4 SHS. Now we're going to select all the columns and assign the column section, and select all the beams and assign the beam section. Now we can check that everything looks alright. We've got 150 PFC for the beams, 75 by 4 SHS for the columns. Step number 2 is to add supports. In this step, we're going to decide on pin or fixed supports. For this example, all my supports will be pinned, which means translation about X, Y, and Z is fixed, and rotation about X, Y, and Z is released. I really like the graphics of this software. It's very beginner friendly, because if you play around with the restraints, you can easily tell what's happening just by looking at these, how do you call these, restrained representation. You know, so a pin support, you can see that it restrains translation about all the axes, and then if we change to a fixed support, you can see these rings denoting that the rotation is also fixed. So let's go back to paint. And step number 3, apply self-weight load case and run an analysis. While in this case, the self weight was automatically added. Not all software do this automatically. So don't forget to add self weight in your model. And before adding any release or extra load cases, we're just going to run an initial analysis. Number 4, check for errors and review bending moment diagram, shear diagram, and axial force diagram, and the deflected shape. So no errors popped up after the analysis, which is good. Now I'm going to review the bending moment diagram, shear force diagram, and deflected shape. So ask yourself, are these outputs as expected and within reasonable magnitude? Okay, so looking at the bending moment, because I haven't applied any release, the default connection between members is a fixed connection. Therefore, I would expect a negative bending moment where the beam meets the column. Shear force diagram looks alright. Deflection also looks fine. It's only under self weight, so I wouldn't expect any large numbers. Let's see what this 3D button does. Well, that's pretty cool. You can tell which face of the element is in compression or tension, right? It looks like the bottom fibers of the beam are trying to open. That's pretty cool. Now, step number 5, verify reactions. So we have to ensure that the sum of the structure's self-weight matches the sum of the reactions. So if I click on the beam, each beam weighs 0.69 kilonewtons, so 0.69 times 8 beams plus, if we click on the column, each column weighs 0.25 kilonewtons, so 0.25 times 8 divided by 4 supports, that's 1.88 kilonewtons. Each reaction, cool, that looks alright. If the structure is not symmetrical or has a different geometry, obviously my structure was pretty simple, you can separate in parts and roughly check if the reaction value is reasonable. This is just an extra step to make you more confident that you are doing things right. So step number 6, release member ends gradually. So we're going to release the ends of the beams one at a time and rerun the analysis at each stage. 3D models involve 6 degrees of freedom in each node, which is 3 translations and 3 rotations. So every element have 12 degrees of freedom, which means that a beam can now spin around its own axis. It can move into and out of the page, which are situations you don't have in 2D software because it automatically restrains those movements. So you want to catch errors early before you mess up with the whole model, and then you have to go back and trying to find where you made a mistake. If you're confident enough with releases, by all means, release all the nodes at once and run the analysis. So let's start releasing the beam ends. Any software will provide you with default standard releases like pinned or fixed. So for example, in Structural Toolkit, you can release the members by right-clicking the member and release pinned. Again, the graphics are quite intuitive. You can see the pins in every node. Now we're going to run an analysis. It looks good. Now you can do the same thing for each beam and rerun the analysis at each step. I'm just going to release all the nodes to speed up things. All connections will be pinned. You can also change restraints straight from this table. So F is for fixed, R for released. I personally would recommend you changing from the table because this way you really have to know what you're doing. For example, for this beam, I'm fixing translation about X, Y, and Z, so F, F, F. And remember, I'm looking at local axis, which is different from global axis. I'm fixing rotation about X axis, so that's F, which means the beam cannot spin around its own axis. I'm going to fix Y rotation, and finally we're releasing the Z axis. So my thumb points towards the direction of the axis, your thumb points up because it's a thumbs up. Did you get that? That was funny. Come on. Yeah. And my fingers towards the direction of the forces. My thumb is pointing towards the Z axis. If I want to release this rotation of the beam, I need to release rotation around Z axis. You probably learned the right hand rule. Now let's run an analysis. And notice that I have released rotation in all ends of the beams, and after running an analysis, I didn't get any errors. So typically other software won't let you do this. They will require you to restrain the movement of the structure in all axes. For example, this same model in space gas, if we run an analysis, this error of instability along Z-axis will pop up on the screen. If you apply a support restraining movement in Z and rerun the analysis, another instability error will still pop up on the screen. Now you have to restrain movement in X, and only then the model will run without instability errors. So basically most software will require manual restraint to work in a 3D scenario. I think Structural Toolkit automatically adjusts restraints or remove unnecessary degrees of freedom, which simplifies the user's work. But at the same time, just be aware that most software won't do that. So step number 7, add load cases and combinations. So we're going to introduce this step by step and rerun the analysis. I'm just going to add a 1 kilonewtons per meter UDL on these beams. I already have a 1.2 G plus 1.5 Q load combination. Step number 8, perform sense checks. So we're going to review again the reactions, the bending moment diagrams, shear force diagram, and deflected shapes. So if I display the bending moment diagram, all the connections are pinned, so I shouldn't see any negative bending moment. Shear force diagram, and then deflection shapes. If we look at the 3D view again, notice that now that we have pinned connections, the columns are not carrying any bending. Therefore, the deflected shape is much different from what we had in the 3D view before. We had an S-shaped column deflection. Step number 9, address warnings and errors. Don't ignore them. Ensure that you understand their meaning. In this case, we didn't have any errors because it's a quite straightforward frame, but do not ignore them unless you really know what you're doing. Step number 10, differentiate between global and member deflection. We're going to focus on member deflection when checking against code limits. So if you're checking the deflection of a beam against the code limits like span divided by 250 or span divided by 360, you should use the local deflection. So if we run a beam in between these two beams and run an analysis, the global deflection is different from the local deflection, right? Because the global deflection will account for the deflection of the beams supporting this beam. The local deflection is as if we applied supports at both ends of the beam. So if you can't find the local maximum in the software that you're using, the trick is to restrain the vertical movement of the ends of the beam, and then you will get the local deflection of that beam. Let's have a look at another interesting scenario. So imagine we have an extra column here. I'm just going to paint this column. And then let's apply some extra loads on these two beams. So I'm going to rerun the analysis. You can see that the bending moment here is smaller than here. The deflection is also smaller. Notice that it looks like the shear force for a continuous beam. If I look at the axial force diagram, we can see that this column is in tension. Therefore, it's supporting this beam. It's not loading the beam. So what's my point? That yes, you might use a smaller beam underneath, because maybe the architecture design intent didn't allow for much space in the floor framing, and there's a greater clearance in the roof framing, so I will use a larger section up in the roof framing and a smaller section in the floor framing hanging off this column. That's what you would understand by reading these diagrams, but at the same time you have to make sure that the builder will be able to prop the floor framing while the column is not in place. You have to make sure that the beam can withstand construction loads without the column in place. Those are little details that I like showing students so that they can understand the load paths, they can understand reading diagrams, they can understand making sure that the construction process will be suitable for how you design the structure to behave. Play around with it. Let's say, for example, if I make this beam very stiff, let's say a 460 UB, and then check the axial forces diagram, the column is not in tension anymore, it's in compression. Okay, so I changed the stiffness of the beam, I changed the stiffness of one beam, and now the structure is behaving completely different from before. So be curious and, try to have fun with the structure. So today we covered how to choose the right structural engineering software for your needs, and I walked you through my beginner step-by-step process of learning a new program from scratch. Let me know in the comments what challenge you have faced when learning a new software, and if you found this video helpful, I would definitely watch this one next.